Good morning. Now, this is our third class on oscillations. Here, our aim is to derive the expression for energy of a particle executing simple harmonic motion. Okay, so in the last class, we have studied what is simple harmonic motion, and any particle executing simple harmonic motion is called a simple harmonic oscillator. Okay. Now here our aim is to find the final expression for total energy of a particle executing simple harmonic motion. Total energy means sum of kinetic energy and potential energy. So first we have to derive an expression for potential energy and then for kinetic energy, and then we have to add that. Then only you will get the expression for total energy of the simple harmonic oscillator, and finally you will represent it graphically. So this is one of the possible essays from this chapter, Oscillations. It is easy to learn also. So let's start. Now, as I already said, we know energy of a particle executing simple harmonic motion has potential energy. Where does this potential energy come from? Potential energy comes on account of its displacement from mean position. That is, if a particle is in mean position or equilibrium position, once it has a displacement, then that work that we have done in order to displace the particle from the equilibrium position will be stored in it as potential energy, that you have studied in your lower classes. Now what about its kinetic energy? It comes from its state of motion. Okay. Now the magnitude of both potential energy and kinetic energy will change or will vary during motion. However, their sum will always be a constant, and that occurs only if frictional force, viscous force, etc. and all is absent. Now let us derive the expression for potential energy first. As I already said, potential energy arises from the work done in displacing a particle from its equilibrium position against a restoring force such as frictional force that try to bring it, which is then stored in it as potential energy. So, when a particle is displaced from its equilibrium position, that is, in order to displace a particle from its equilibrium position, we have to do work, right? Now that work is actually done against frictional force. Now that work that we do in displacing the particle from its equilibrium position against restoring force is stored in it as potential energy. Okay, now suppose that the particle is displaced through a distance x and let F be the restoring force. Then what will be the small work done? Work is actually force into distance, right? But since we are going to consider a small displacement, say dx, then the work that we are considering also will be small, say dw. So dw will be f dx. Negative sign indicates that that work is done against restoring force. That is why negative sign is put there. Okay, now what is this force? Force is mass into acceleration, m into d square x by dt square. Okay, if x is the displacement, dx by dt is the velocity, and d square x by dt square is the acceleration. So, in place of this f, you are writing mass into acceleration, m into d square x by dt square. Dx is kept as such, negative sign is also kept as such. Okay, but in the last class, we have already studied an expression for acceleration of a particle executing simple harmonic motion. What is it? Alpha is equal to minus omega square x. Alpha is the acceleration, and its expression that we have studied in the last class is minus omega square x. Okay, so in place of this acceleration d square x by dt square, you can write this value minus omega square x. Now on substituting this in the above equation, this negative and negative will become positive, and what is left behind will be dw equal to m omega square x dx. Okay, so that is the small amount of work dw done in order to displace a particle through a small distance, say dx. Now in order to find the total work done, that is capital W, what do you have to do? You have to integrate this from 0 to x. That is capital W is equal to integral 0 to x of this one, m omega square x dx. Okay. So here on integrating, what happens? M omega square is a constant, right? We can take it outside. What is remaining is 0 to x, x dx. What is integral x dx? X square by 2. So it will be m omega square x square by 2, which is half m omega square x square. This is your expression for potential energy. It is denoted by capital letter U. U is equal to half m omega square x square. Okay, so you got the expression for potential energy. Now what you need next? You need to find the expression for kinetic energy. Kinetic energy, as I said, it arises due to the motion of a particle. Suppose that v is the velocity of particle when the displacement is x, then what is the expression for kinetic energy? It is half mv square. Okay, but in the last class we have already derived an expression for velocity of a particle executing simple harmonic motion. What was it? V is equal to omega into root of a square minus x square. Okay, just as that we derived for acceleration alpha minus omega square x, we have derived an expression for velocity also, which is v equal to omega into root of a square minus x square. Just substitute this value of v in this equation. Then your T will become, that is T stands for kinetic energy, it will become half m omega square into a square minus x square. Okay. Now you have got the expression for kinetic energy and potential energy. So what will be your total energy? Capital letter E, kinetic energy T plus potential energy U. This was your expression for kinetic energy and this was your expression for potential energy. Expand the first term. So on expanding, this x square term, this one will get cancelled and what remaining will be half m omega square a square. This is a constant. This means that the total energy is independent of displacement of particle and is same throughout the motion. Why? Because it is independent of displacement. Here you cannot find any term x. So since this term is independent of x, independent x means displacement, we know that the total energy, even though potential energy and kinetic energy varies during motion, their sum, that is total energy, will always be a constant because the expression for total energy contains only constant terms. It does not have the term x, which is displacement. Okay, all these are constants: mass constant, omega, angular frequency constant, amplitude constant, everything. Okay, now here next step, what they have done is they are going to find the average value of potential energy. What was your expression for potential energy? U. Average, in order to denote, you put a bar sign over that. So it will be, how to find the average potential energy? Expression for potential energy was half m omega square x square. You just integrate from 0 to time period t and divide it from integral 0 to t dt. This will give you the average value of potential energy, which is u bar. Okay, here the constants are m omega square by 2, so take it outside. Okay, m omega square by 2 is taken outside. Now what is remaining in the numerator? It is 0 to t x square dt, right? So 0 to t integral is kept as such. In place of x, you are substituting a sine omega t, because this we know this is a solution for simple harmonic oscillator, or the expression for displacement. So in place of x, you just substitute the value a sine omega t. Since it is x square, it will be a square sine square omega t. Okay, rest everything is kept the same. Now m omega square by 2 is kept as such. Here a square is a constant that is taken outside. Now what is this one is denominator is kept as such. What is there in the numerator? Integral 0 to t sine square omega t dt. Right? What is sine square omega t? There is a trigonometric relation, that is 1 minus cos 2 theta by 2 is sine square theta. Right? Here your theta is omega t. So what is sine square omega t? 1 minus cos 2 omega t by 2. That is what which is written here. Okay. Now on simplifying, you will get the final answer. The average value of potential energy U bar as 1 by 4 m omega square s square. Similarly, you have to find the average value of kinetic energy also. Procedure is the same. This was your expression for kinetic energy. Average value means T bar. Then integrate from 0 to T. Denominator is kept as such here. Then half m omega square a square dt. Here you are just splitting this integral, okay, into two parts, because here you have a minus sign. So you just split this integral. That is the first term as 0 to t half m omega square a square dt by integral 0 to dt. Then integral 0 to t half m omega square x square dt by integral 0 to t dt. In place of x, as before, you just substitute a sin omega t. So since it is x square, it will be a square sin square omega t. Okay. Now on simplifying, you will get this also as 1 by 4 m omega square a square. That is the average value of kinetic energy T bar and the average value of potential energy U bar is found to be the same. That is 1 by 4 m omega square a square. Okay, and it is a constant also because it does not involve the displacement term x. Now this is a graphical representation. That is, in this graph they have represented the variation of potential energy and kinetic energy with displacement. The graph is having a parabolic shape. Now the total energy, that is T plus U, is represented by a straight line parallel to the displacement axis, that is parallel to x-axis. Now from this figure, what can you infer? When the particle is at the mean position, that is at equilibrium position, that is at x equal to 0, your kinetic energy, that is the particle's kinetic energy, will be maximum, and that value will be this, whereas potential energy will be 0. Okay, that is a situation when the particle is at the equilibrium position, x equal to 0. Now when the particle is at the extreme position, that is at x equal to plus or minus a, then just the reverse happens, that is kinetic energy will be 0 and potential energy will be maximum with the value half m omega square a square. So when you draw this graph, you have to write this explanation also. This explanation and graph is very important. Okay, so with that we have come to the end of finding the energy of a particle executing simple harmonic motion. So when you are asked to derive that, you have to derive the whole thing including this graph and its explanation. Okay, so up to this much is an essay, right from the beginning till here. Okay, now next one, here I am presenting only a concept, define free oscillation. It is simple, that is, you know, a simple pendulum, the bob of a simple pendulum. This one, this is the bob of a simple pendulum. Suppose that it is oscillating in vacuum and you are displacing it from its equilibrium position and you are letting it free, then it will execute simple harmonic motion. And here, since it is oscillating in vacuum, there is no loss of energy because there is no frictional force, nothing like that, because it is oscillating in vacuum. So the pendulum, what will happen, it will continue to oscillate with the same period and same amplitude for any duration of time. Why? Because it is your pendulum is in a vacuum condition, there is no dissipative forces. You are displacing it from its equilibrium position and you are allowing it to oscillate freely. In such cases, it will oscillate for any duration of time with same period and same amplitude. That is, its energy will always remain as a constant. Such oscillations are called free or natural oscillations, and the frequency of oscillation is called free or natural frequency. Okay, so from today's session, the two important questions are: one is an essay question, that is, derive the expression for total energy of a particle executed in simple harmonic motion. In that case, you have to start from the beginning and write up to this much. And the other one is a definition, that is, define free oscillations. Okay, for today that is enough. Thank you.